Hey everybody. Today we're doing some example problems using the central limit theorem. The central limit theorem describes the sampling distribution of the sample mean, x bar. A bit more specifically, suppose we have simple random samples of size n that are drawn from a population with a known mean, mu, and known standard deviation, sigma. If n is large, and 30 is pretty much always sufficient, then the sampling distribution of x bar is approximately normal with mean mu and standard deviation sigma divided by the square root of n. In other words, the sample mean x bar has the same expected value as an individual draw from that distribution, but less variability. An addendum to this, if the population distribution is exactly normal, then the sampling distribution of x bar is exactly normal, regardless of the sample size. So notice that the central limit theorem doesn't say anything about the shape of the distribution we're sampling from. It just specifies the mean and the standard deviation. Problem 1. A distilled water dispenser vends liters of water according to a normal distribution with mean 1.03 and standard deviation 0.02. So you push the 1 liter button on this machine. On average, you get a little more than 1 liter, but there's certainly variability in this dispenser. What's the probability that a single liter dispensed is actually under 1 liter? What's the probability that 10 liters average less than a liter each? What about for 100 dispensed liters? So I recommend pausing the video here, trying these problems, and then watching my solutions. So we compute normal probabilities in each of these cases using the cumulative distribution function, or CDF. And in R, which is my technology of choice, that's represented by the p-norm function, and we'll specify the value of interest, the mean, and the standard deviation of the normal distribution that we're looking at. So for part 1 of this example, we're looking at normal distribution with mean 1.03, standard deviation 0.02. We're interested in the probability of getting a random value less than 1.0. So we're going to do p-norm of 1.0, comma 1.03, comma 0.02, and we get a little bit less than 7%. Now imagine getting 10 liters and looking at the sample mean. On average, we expect to get 1.03 as the average of those 10 liters, but sometimes it'll be a little bit higher, sometimes it'll be a little bit lower. The standard deviation of the sampling distribution of x bar is going to be 0.02 divided by the square root of n. The variance will be 0.02 squared divided by 10, and that's by the central limit theorem. In this case, the distribution of x bar for a sample of size 10 is going to be exactly normal because we're sampling from an exactly normal distribution. So, to find the probability of getting a sample mean less than 1 in this distribution, we do the same p-norm command as before, we just have to feed it the new standard deviation, 0.02 divided by the square root of 10. In this case, we get 0.0001%. So if I were to draw a picture on this one, the bell curve that I drew would have the same center as in the previous example, but a lot less spread. So relatively speaking, the value 1.0 is much more extreme in this distribution than in the one from the first part of this problem. Similarly, for n equals 100, the sample mean has the distribution with that same center, 1.03, and a variance of 0.02 squared divided by 100. So a standard deviation of 0.02 divided by 10, divided by the square root of 100. So the probability that x bar is less than 1 can be computed in R using the command p-norm of 1, comma 1.03, comma 0.02 divided by the square root of 100. In this case, we get 3.7 times 10 to the negative 51st power, so an infinitesimal number. In summary, it's somewhat unlikely that a single liter will be underfilled. So, 6 or 7% chance that you get shorted on 1 liter. On the other hand, it would be extremely unusual if the mean of 10 liters were less than 1. So on average, if you get 10 liters, you aren't going to get shorted, except in very, very rare circumstances. On the other hand, it's statistically impossible to get a sample mean of 100 liters that would be less than 1. The probability, something like 10 to the negative 51st, just isn't going to happen. Example 2, again, pause the video, give this one a try before advancing. The weights of bags of a certain brand of candy are normally distributed with mean 45 grams and standard deviation 1.5 grams. So find the probability that one randomly selected bag contains more than 46 grams, that 5 randomly selected bags contain an average of more than 46, and the probability that 25 randomly selected bags contain an average over 46. So this is going to be pretty similar to the first problem, except that now we're looking for a right-tailed probability. We want the probability of getting results bigger than 46. So to start, for an individual draw, to get the probability that x is greater than 46, we're doing 1 minus the probability that it's less than or equal to 46. And that's another p-norm command. Overall, I'm doing 1 minus p-norm, 46, 45, 45 being the mean, 1.5, 1.5 being the standard deviation. Overall, I get about 25.2%. That's the probability that a single bag is overfilled by more than 1 gram. In other words, a weight of at least 46 grams. Now looking at the sample mean for 5 randomly selected bags. We're using the essential limit theorem again, so the sample mean x bar is going to have a normal distribution. Its mean is going to be 45 grams, and the standard deviation is going to be 1.5 divided by the square root of 5 grams. So the variance would be the square of that. Again, I'll do the probability of getting x bar greater than that by doing 1 minus the probability of getting one less than that. 1 minus p norm, 46, 45, 1.5 divided by the square root of 5. So it's about a 6.8% chance that when you get 5 bags, on average, they're overfilled by more than 1 gram. Finally, when you have a sample of size 25, the standard deviation gets even smaller. The center, the mean, stays the same, of 45, but now the standard deviation is 1.5 divided by the square root of 25, so it's down to 0.3. We do the probability that x bar is greater than 46 by doing 1 minus the probability that it's less. 1 minus p norm, 46, 45, 1.5 divided by 5. We get about 0.0004. So there's only about a 0.04% chance that 25 bags are overfilled by more than 1 gram on average. Last example. Accidents along a dangerous stretch of highway occur at a mean rate of 2 per day with a standard deviation of 1.5 per day. So here's the full probability distribution. So looking at this, you can estimate that the probability that there are no accidents on a single day is probably about 14%, just estimating from looking at this graph. What's the probability that more than 10 accidents occur in a week, that more than 20 do? So again, pause the vid and give this one a try, but notice that I'm asking about 7 days, even though the plot only shows the distribution for single days. So watch out for that distinction. Okay, so even though we're given a full probability distribution for a single day, we can't easily infer the distribution of accidents in a week, 7 days. So we're going to need the central limit theorem, and in this case, the central limit theorem for 7 days is going to give us an approximation, unlike in those first 2 examples where it was exact. Now, we were asked about the number of accidents in a week. The central limit theorem refers to means. So what I first want to do is to translate from one of those terminologies to the other. And the basic way we're going to do that is to say that if you have n accidents in a week, that's the same thing as having an average of n over 7 accidents per day. So on any given day, we have a population mean of 2 and a standard deviation of 1.5. So the sample mean, when you have a sample of size 7 over the course of a week, is going to have the distribution approximately n of 2.0, 1.5 squared over 7. So the standard deviation is going to be 1.5 divided by the square root of 7. And the probability of getting a sample mean greater than 10 sevenths, which is the probability that there are more than 10 accidents in a week, is 1 minus the p-norm of 10 sevenths, 2.0, 1.5 divided by the square root of 7. So again, to do the probability of getting a value greater than 10.7, I'm doing 1 minus the probability of getting less than. And the probability of getting less than that is the p-norm of that value, and then the mean and the variance. Overall, we get 0.843. Similarly, if we want to do the probability that there are more than 20 accidents in a week, we're trying to find the probability that the sample mean in a sample of size 7 is greater than 20 sevenths. So I'm doing exactly the same p-norm command as before, except now I'm feeding it 20 sevenths instead of 10 sevenths. We get 0.065. The probability of more than 20 accidents in a week is only about 6.5%. And this is potentially helpful if you are planning staffing, for instance, for a emergency response center, like sending out ambulances or tow trucks or whatever. Now, if you've been paying close attention, you might have noticed that the central limit theorem uses the number n equals 30 as sort of a sufficiently large n. And in this problem, the n was only 7. And so technically it kind of seems like we shouldn't be using the central limit theorem at all. On the other hand, the central limit theorem with that n equals 30 is very conservative. And typically the central limit theorem does pretty well for much smaller sample sizes, including n equals 7. And the big exception is if you have a distribution with extreme outliers or a tremendous amount of skew. And if you look back at the histogram here, we do have some skew, but it's not ridiculous. So we should expect our central limit theorem approximation to be okay, just maybe not perfect. So I actually went back and computed probabilities exactly from this last example. So I said it was hard to get a distribution for the number of accidents over the course of 7 days, but it's not impossible, and I did that in math. I did some code for that, and I got these numbers. For the probability that x bar is greater than 10.7, the exact probability is 0.813. The central limit theorem approximation was 0.843. So we were off by about 3 percentage points. Similarly, for more than 20 accidents in a week, the exact probability is 5.6%, and we got 6.5%. So we're off by a little, but not by an extreme amount. Not bad for the central limit theorem approximation, considering how little work it actually took us. The computation was extremely simple compared to the computation I had to do for those exact probabilities.